Okay, hi, I'm Gil-Ho Lee from Postec. Thank you very much. It's my pleasure to share our recent work with experts. Okay, so this work is about generating some Floquet state in device level. So I'm doing nano device experiment at low temperature. So I'm using graphene in contact with the superconductor, making Josephson junction and applying light. In our case, the light was in the microwave range, so it's not optical measurement. So thanks to the previous speaker, Professor Oka, so I can smoothly start my talk. So as a condensed matter physicist, we all want to control the band structure of the material because that governs the property of the material. So you can make some new structure of the material or twisting the same material in some magic angle, making a graphene into superconductor, or applying pressure to make a room temperature superconductivity, or you can shine the light on the material to temporarily change the property of the material and inducing emergent phenomena. So yeah, Bloch state you have learned in a solid state physics course. So in the existence of this kind of, does it work? Space periodic potential, you end up having this copied dispersion relation along the k-axis. So this is, and then if you turn on the interaction with the ions, Coulomb interaction, that opens a gap. And that's your band gap, and that is your band structure. And this is your first Brillouin zone, and the second one, third one are just a replication of the first one. So we just focus on the first Brillouin zone. And in that way, the K is now called quasi-momentum, because that's quasi-momentum in the crystal, as if the particle obeys the dispersion relationship in that way. So, for example, electron in graphene is still an electron, but it behaves as if it's a massless Dirac fermion, right? And also in various topological material. And in time-periodic potential, we can have this Floquet state. Now the copy happens along the energy direction. So this energy axis is called a quasi-energy, and that is basically our Brillouin zone along the energy direction. And in some people call it Floquet-Bloch State. This kind of a Floquet engineering, at least to me, it was not so familiar before doing this our work. So when for AMO people, they shine laser onto atoms. So that's very natural platform for study of Floquet state. So quantum state of the atom is affected by the interaction with the light. And people now have some idea to make some topological material from non-topological material, shining circular polarized light as introduced. And in condensed matter systems, so people use this kind of technique, so-called Floquet engineering, to do some quantum information as well. For example, in this kind of quantum spin qubit, for example. So by tuning the frequency of the light, intensity of the light, or polarization of the light, you can control this kind of Floquet state as you want. That's wonderful as an experimentalist. So you can shine some circular polarized light to break the Simon-Boson symmetry to make non-topological to topological one. Or even people are thinking about using this Floquet engineering to do some braiding operation for non-abelian anyons. For example, you don't have to really braid in the real space to make this topological superconductor, topological quantum computer. As far as you can braid this non-abelian, so-called non-abelian, for example, the Majorana fermion, if you can exchange these two, this excitation in some abstract space, in parameter space, that's good enough. So people are thinking about this Floquet engineering for doing that kind of braiding operation as well. So there are not so many, compared to the AMO field, not too many experiments done for this Floquet study in condensed matter system. So one of the example is from Professor Lugetik's group at MIT, 2013 and 15. They shine pulsed mid-IR optical light, which has the frequency of 30 terahertz, and measure this time-resolved RPAS to see this the topological surface, Dirac surface, is actually can be replicated along the energy direction. But the light was pulsed so that the Floquet state can stay on order of hundreds of femtoseconds. It will get back to the equilibrium point when the pulse ended. So I think one of the reasons is that they would need very strong electric field to induce this Floquet state. So that's why we need to use this pulse light to compress the energy into a certain period of time. And even we have this ability to apply this strong electric field light continuously, the sample would be melted by this strong power. So the important parameter for thinking about the Floquet state is this beta parameter, which is basically normalized electric field divided by frequency square. So that governs how strong the interaction of the Floquet states are. So as you can see clearly, as the frequency increases, the needed electric field to have strong enough interaction to see the Floquet state increases square. So our idea is rather simple. So we decrease the frequency of the light from 30 terahertz, say, to 10 gigahertz by 3,000 times. Then the needed electric field will be reduced by 10 to the 7th. Then the heating will be reduced by 10 to the 14th. Then maybe we can shine continuous microwave without heating the sample too much and see the Floquet state for indefinite time as far as we shine the light. But downside is that if we decrease the frequency of the light, the gap between the original state and the Floquet state will also reduce because that gap energy is determined by HF. So we need 3,000 times better energy resolution spectroscopy method to see that. So that's why we worked on this making superconducting tunneling spectroscopy technique in device level. So this is basically STM, scanning tunneling microscope technique. We're just mimicking the STM technique, but we just cannot sweep the tunneling probe around the sample. We just put tunneling contact to the material to locally see the density of state near this contact. So, okay, there are many attempts to use this tunneling spectroscopy to study the 2D material. For example, from Geim's group, maybe, okay, I'm not sure, but anyway, so people have used the boron nitride as a tunneling barrier between two graphene, and by changing the twisting angle between these two, we can expect different kind of spectrum. And they even show this negative differential resistance as well. And people use this kind of technique to see the Landau level formed in the graphene under strong magnetic field. And in Pablo Herrera's group at MIT, used this tunneling spectroscopy to see the so-called underbound state inside of the graphene Josephson junction. That I will focus on, so I will explain it more into details later. So our idea is not using the boron nitride or other material. We just try to use the naturally forming insulating, a tunneling barrier. So if you are working on the superconducting, if you have worked on making superconducting contact to the graphene, you must know that we always need this kind of adhesion layer, titanium adhesion layer between the graphene and superconductor aluminum, for example. Because unless you have this adhesion layer, you will have, you end up having this like a few electron volt height tunneling barrier. So that will make a bad contact, which is bad for people who wants to induce the superconductivity into the graphene, because the graphene itself is not superconductor. But our idea is to use this bad contact as a tunneling contact. So we just try before going that, and plus our superconducting tunnel contact is made of superconductor, so that's better. We'll have better energy resolution compared to the normal tunneling electrode. If you see, for example, if you are to study the density of state of some superconducting niobium diselenide, you can either use the normal STM tip or superconducting STM tip, but the superconducting STM tip has very sharp density of state in energy. So you have better energy resolution because the DIDB, the differential conductance peak, will happens only when this sharp density of state peak aligns with some feature inside of this niobium diselenide density of state. So that's one another good thing for using superconductor as a tunneling electrode. So when we make an ohmic contact, so-called good contact to the graphene, when we first encapsulate graphene with boron nitride to make a graphene very clean, and we etch one side of the graphene to expose fresh 1D edge of the graphene, and we put usually titanium as an adhesion layer and put aluminum. And then this superconductivity from the aluminum can be well induced into the graphene because they form a good transparent electrical contact. But in our case, we put aluminum directly onto the graphene. It's like a Columbus egg. You just try it, and then we saw the well-behaving, tunneling contact actually. So this is the graphene encapsulated with boron nitride, shaped into the rectangular shape, and then we put aluminum side contact directly to the graphene. And you can view this superconductor as a superconductor, of course, and then the graphene as a normal metal. And you expect this kind of tunneling spectrum because it's basically the cross product of the density of this material and the density of states of that material. And that material has the flat density of state. And if we fit it with the BKT theory, we get reasonable number of superconducting gap and electron temperature. And moreover, the Dines parameter, which tells us the smaller the better, smaller the longer the quasi-particle lifetime is in the superconductor. So, which means good, okay? And we have this, we can see this sharp density of state peak, which is good. And this is our method to see the density of states of some material, and I will talk about what material, what kind of system we want to look at. That is under bound state. So when we put superconductor right next to a non-superconducting material, the superconductivity can be induced into the non-superconducting material. This is called the superconducting proximity effect. And if we put two superconductor right next to the normal metal, these two wave function from the superconductor can form some kind of coupling. This is called Josephson coupling. If that happens, the supercurrent can flow through the normal metal, which is not superconductor. But more microscopic point of view is looking like this. So in particle in a box, when the particle electron inside of this potential well, when it goes this round trip, the accumulated phase will be 2kL. If that is equal to 2 pi n, n is the integer, then you will end up having stationary state. So that's your eigen state. That's what you solve in a quantum 101, right? And then our Josephson junction can be also viewed as a particle in a box. But now the barrier is the superconducting gap, not just the insulating gap. So if your electron energy is smaller than the superconducting gap, then the electron just cannot get into the superconductor, but it can grab another electron which has the opposite energy by forming a zero energy Cooper pair, so it can get into the superconductor, but it will result in reflecting a hole because this electron grabbed this electron, so it will result a hole reflected along the other direction. This is called Andreev reflection. And the hole can also go under, another Andreev reflection, getting back as an electron into the original state. When that happens, one round will transfer one Cooper pair from left to right superconductor. This is how Josephson current can flow. And the phase accumulation for this electron can be written in that way. On top of this dynamic phase, you will have also superconducting phase. This phi is the phase difference between these two superconducting electrodes, okay? Which we can control. And that will give us this interesting shape of under a bound state spectrum, which can be tuned by the phase difference phi between these two superconductors. So that's our bound state we want to look at. So we made this kind of device by putting two ohmic contact superconductor into the graphene to make a Josephson junction and make a ring and apply magnetic field to control the phase difference between these two superconductors, okay? And then we put side tunneling contact using another aluminum electrode onto the side of the graphene, and then we measure the density of DIDV curve of this tunneling probe as a function of external magnetic field, which tune the phase difference. So you see that the periodic oscillation of this DIDV peak, each peak comes from the lower and upper under bound state that I just showed you. Okay, this is good. This looks the peak looks sharp enough for us to do something more interesting. This is just the temperature dependence. So as we increase the temperature close to the TC of ohmic contact aluminum, the underbound state disappears as expected. And on top of that, near the TC, additional peak appears, which comes from originally empty state of upper underbound state. But at high enough temperature, the upper underbound state will be also partially filled due to the thermal excitation, and we are seeing it at high enough temperature. Okay, then we shine the microwave. We shine the light by because this is a gigahertz range. We used a coaxial cable that you use for TV, right? The coaxial cable is fitted into the fridge, minimizing the thermal load from the room temperature. And we just put this center pin of the coaxial cable nearby the sample, like 1 centimeter away. This is very poor antenna, but it's, as far as it works as antenna, we were okay at that time. So this is our way to shine the microwave. Obviously, the microwave will not be polarized. So you can think the microwave is unpolarized for now, but with well-defined frequency, but with also the amplitude. So yeah, so as we increase the microwave power, you would expect that the field under bound state is copied with Floquet state, and empty under bound state will copy it as an empty Floquet state. So I'm drawing the not the density of state, but the spectral density. So I just want to point out this. And as power increases more and more spectral density from the original state move to the Floquet copied state. So that the sum of this colored area should be always constant, which is called sum rule. This is experimental data. When the power is small enough, you will have only one pair of underbound state, as you see previously, and increase the power. Of course, the frequency was fixed to 12 gigahertz. HF corresponds to 50 micro EV. Okay? So as power increases, the original underbound state peak decreases as the spectral density decreases, but the side peak appears here and also here, and if you have a good eye, maybe here, maybe not. So if I take a line cut here, you can see the original underbound state and the replication of that underbound state with the peak distance of 50 micro EV, as we expected with the frequency of 12 gigahertz. Okay? And I just want to, at this point, I want to emphasize that this measurement was done with continuous shining microwave. So the fact that we were able to still see the density of state, the graphene electron temperature was not heated too much. So it was cold enough for us to see the underbound state spectrum as well as the Floquet state spectrum. Okay, so because we were able to make this Floquet state, how do you say, steady enough, so we can take our enough time to measure the details of the spectrum. For example, if we shine 12 hours of microwave, we can make the Floquet state lifetime, Floquet state for staying for 24 hours, for example. Just for sanity check, that replication is really coming from the underbound state. We also apply magnetic field, and this is the original underbound state oscillates as a function of external magnetic field that I showed in the previous slide. And replicated state also oscillate in the same way. So that probably comes from the original state that is oscillating as a function of magnetic field. That's another one way we can check that the additional DIDV peak is actually is related to the original state. Sum rule. So we integrated the IDV curve as a function of voltage, and that is basically the area of this DIV curve. As we change the power of the microwave, we just plot the area of this DIDV curve. That is almost constant. Except there's a slight decreasement as power increases, and we think that is just due to the fact that our voltage integration is done within the finite voltage range. Okay, so we didn't measure the voltage spectrum higher than 0.5 millivolts. So if the Floquet state appear at even higher, although we cannot resolve here, if the Floquet state appears at higher energy state, then that will contribute the leaking of density of state away from our integration range. So I think that's just an artifact. So if we were measured larger range, that decreasement can be cured, I think. So that's one thing we were able to do because we shine the continuous microwave, we can measure the details of the spectrum, so we were able to confirm this sum rule. Okay, and for going further, with collaboration with Professor Gil-Ho Lee, who at the same university, and also one of his students, we were able to fit it with theory. So at least theory suggests that the spectral density of the Floquet state, for example, for nth Floquet state, should follow the Vessel function of n square here. But here, beta is normalized strength that I described you. It is given by electric field divided by frequency square. And zeta is the polarization angle. But because we think the microwave light was not polarized, we just average it out. And that gives us this theoretical lines as power dependence. And these are data, and the solid lines are theoretical calculation, which fits okay. And the line cut looks even better. But anyway, I think when we are fitting this, our electric field was order of 1 volt per meter. As compared to this 30 terahertz mid-IL pulse light case, the electric field was 10 to the 7th volt per meter. So as expected, the needed electric field was indeed reduced by a factor of 10 to the 7th. Okay, this is a little bit of details of the theoretical calculation. So on top of a delta function like under bound state, we also needed to consider the proximity-induced superconducting gap inside of the graphene inherited from the ohmic contact superconductors. Okay? By doing so, we were able to fairly reproduce what we have measured experimentally. For the last test was changing frequency, of course. If you change the frequency of the light, you would change the gap between the Floquet state and the original state. So if we decrease the frequency from 12 to 3 gigahertz, you can see the distance between these peaks decreases and to the level that we start to lose the resolution with so our energy resolution was order of 20 micro eV. But within that range, the delta V, which is the gap energy between the Floquet state and the original state, was proportional to the frequency with proportional constant Planck constant. Okay. Yeah. So I just want to note that what we just observed is the replication of spectrum of the quantum state with the tunneling spectroscopy when the light is shed. But there's another explanation mechanism which can give this kind of result, which is called the Tien-Gordon effect. That is basically the inelastic inelastic tunneling. So for that scenario, the electron or hole that is coupled to the light is actually the tunneling electron from superconductor to the material. So in our Floquet picture, the electrons that couple to the light is the electron inside of the graphene. So that the density of state of the inside of the graphene, in our case Josephson junction, replicated, and we were just observing this replicated density of spectral density using this tunneling probe. But if the electron that is tunneling through the barrier is coupled to the light, it can absorb or emit energy, undergoes which can result in this inelastic scattering, which can give same result. But at least in our estimation, the electric field that we would need to explain our result in this Tien-Gordon effect is order of magnitude higher than we applied. So we know how much light we applied because we are the one who applied the light with the microwave source. We were able to estimate this electric field, and that cannot explain this replication of the spectral density in terms of the Tien-Gordon effect. But obviously, we need to do more work, especially the polarization dependence, like the Nugetics group did in 2015, I think. Yeah, but we're not still there. What we are these days doing is to improve the coupling scheme between the antenna and the graphene. So previously it was very lousy way to couple the microwave. We just put the center pin nearby the sample by hand. But now we are fabricating on-chip RF antenna so that we can make the antenna, the distance between the antenna and the sample is much closer. So now we can see many replication of the state without heating the sample too much. And if you see, for example, 20 copies of state, that means you have roughly beta equals to 20, which is much larger than 1. Previously, it was order of 1, but now we can have 20 of like a beta equals to 20, order of 20 without heating the sample. And probably that can lead us to more interesting Floquet physics at stronger interaction regime. Another interesting idea is to replace the graphene with more exciting material, topological insulator. Then you can probably make a Majorana zero energy mode. And then you can also use this tunneling spectroscopy to prove it. For example, zero bias conductance anomaly that people have been doing, and showing the microwave to replicate the Majorana state. And yeah, actually, honestly, I have no idea what we can do with that. But we can at least think about it. Yeah. Well, interestingly, Amir Yacobi's group at Harvard made a similar structure. Here they use the mercury telluride, cotton mercury telluride heterostructure, which is basically 2D topological insulator, and made it into Josephson junction and put a side tunneling contact. And by applying right amount of magnetic field, they were able to see the zero bias anomaly, which is the signature of the Majorana state. Yeah, and that indeed is very interesting and related structure. Okay. Oh, okay, I was quite fast. So let me summarize. Okay, so honestly, I was not working in Floquet physics. I just learned it by happen to doing this kind of experiment. I learned a lot from Professor Gil-Ho Cho, who did theoretical analysis. I'm very happy that with this nano device can do something in the non-equilibrium quantum physics. So basically our idea is that by reducing frequency much, we were able to reduce the heating effect even more, so that we can apply continuous light without the heating the sample, such that we can measure the Floquet state for like a in steady state. Okay, so for that, reducing frequency requires us to have better energy resolution spectroscopy technique. So for that, we use this side tunneling superconducting contact to resolve this quantum state. And the theory, at least so far, can fit our data reasonably well. But now, after we hope that after optimizing the antenna structure, and more interestingly, if we apply this resonator, microwave resonator technique that has been developed for the superconducting qubit community, we can use that kind of RF technology to apply polarized microwave into the system and study the polarization dependence as well. Okay, and more, another aspect was this kind of a tunneling technique can be also applied to the other 2D material, including topological insulator and topological superconductors, if there is any. Yeah, and yeah, with that, I will conclude my talk. Thank you very much.
Thanks for the interesting talk. We have plenty of time for questions. Anyone wants to start?
Okay, so thank you very much for the very, very exciting results and the talk. So I have one question related to how this microwave field or the electric field is really acting on your graphene.
Mm-hmm.
Should I consider it really the same as what I was thinking? Like if I like a laser pulse applied to a graphene outside such device, or is there something different or special in your situation?
So I see. In optical range, you can focus your lights into a micrometer size of area, so you can shine light here or light there, or not on the graphene, and see the difference. But the thing is, the wavelengths of this microwave is centimeter size, so we cannot focus into that small range. So we cannot, like for example, spatially raster the sample. Yeah. So we are really shining lights onto the surface of substrate. One thing I can note is that this superconductor, if, for example, if there is a superconductor on top of graphene, then that kind of metal can shield the microwave, and for the graphene underneath it cannot feel. We can do kind of that control experiment. Yeah. Okay. Actually, in fact, we can use this resonator structure to focus our centimeter wavelengths signal into a small range as well. So that's one part of our future work we want to do. Yeah. Yeah. Yeah.
Okay, but also the Fermi energy of the graphene probably it's not at drag point, but somewhere far away.
Mhm.
And since your microwave energy is very, very small, you don't really see the physics of the drag point. Because
Okay.
is this correct?
Yeah, thanks for the comment. So for this experiment I described to you, it's not related to the Dirac band structure of the graphene. So for this one, we just used graphene as a high mobility 2D electron gas. Yeah. So, for example, the work done by MacGyver, they shine the circular polarized onto the graphene and open the topological gap and try to see the edge current. That is our work is different from that. So we just we've made an underbound state inside of the graphene and in this case, the graphene just acts as a conductor, good conductor. And we showed a Floquet replication of that underbound state. Yeah, it's a little bit different story. Yeah.
Okay. Thank you very much.
Thank you.
Is the microwave light focused on the graphene, or is the aluminum also exposed to the microwave light?
It's exposed everywhere. Yeah. The sample size is order of micrometer, and the wavelength is order of centimeter. So we didn't actually control where the microwave hit on. It just it's just shed onto the entire surface of the substrate for now. Yeah.
Then what's your understanding of how the microwave affects the superconductivity?
So the gap energy of the superconductor is larger than the HF of the photon energy. So in principle, all the microwave photons should be reflected by the superconductor. But there will be some portion of the photons get absorbed by and create and break the pairs and make a quasi-particle inside of the superconductor. But the superconductor here is bulky. It has like hundreds of nanometer of thickness. So even that depairing mechanism happens at the surface of the superconductor, we think that would not affect the physics that we are seeing. Yeah.
Okay, thanks.
Yeah. Yeah. But if we use this resonator technique, we can focus microwave onto the graphene only. So we can avoid from that possibly problematic mechanisms. Yeah.
I was just wondering, how much power do you have to actually send down at low temperature? So is it like minus 15 dBm or so?
That's
the output of the amplifier, or is it at low temperature?
Nominal power at the room temperature microwave source was order of minus 10 dB. And RF attenuation is order of 50 to 100 dB.
Okay, yeah.
And the coupling efficiency between antenna and the sample would be very poor. Yeah. And I don't remember the exact name in dB, but electric field for the sample actually field is order of 1 volt per meter. To tell the more details, so the way we estimated the actual electric field the sample felt was to measure the Shapiro step, which is the result of the resonance between the AC Josephson relationship and the microwave. From that, we can also seek Vessel function like power dependence. From that, we were able to extract the actual electric field that sample actually is feeling. Yeah.
I see. Yeah, really quite sensitive.
Thank you.
Okay, I've got one. So you said you think the microwave is unpolarized. So can you move the antenna within the refrigerator and see any effects?
Yeah, that's what we want to do actually. Yeah, we need to. Yeah, we never try polarize the microwaves yet. There are two ways: free space, like a really horn-like antenna microwave inside of the dill fridge, but rather rather than that, we would like to use the resonator structure that qubit people have developed. Yeah, they spend a lot of time to develop it, so we just use it for our purpose. That's our plan for now.
Thanks. Any last questions? If not, we can discuss further over the coffee break. So let's thank the speaker.
Thank you very much.